In the last video, we focused on describing an object's motion by graphing its position or its displacement over time. But part of the process there was talking about how fast the object is moving. So that whole time we were referring to this idea of velocity. In this video, we're going to talk about how can you graph that velocity on a similar sort of graph, a velocity versus time graph. So before we can really get into that, just like we did with displacement, it's important for us to talk about what is the definition of velocity if we're going to be referring to it in a graph. And speed and velocity are two terms that we often use pretty interchangeably in our everyday lives because they do have a very similar meaning. In physics, however, they have a really important distinction to them that's important to be aware of. Speed is going to be the rate of change of position. It's how fast an object is moving. Now, the speed is always going to be positive. You can't go a negative speed. Um, just like in your car, your speedometer will never go negative, even if you're going in reverse. You can only have a positive speed. Now, velocity is speed with direction. So you might talk about velocity as like you're going 5 miles per hour north. But more commonly, the way we're going to see this direction play out in our velocity is that our velocity could be negative. If you're going backwards, we say that it has a negative velocity. That positive or negative is in itself expressing a direction that's going to be really important when we refer to this idea of how fast. So that idea that something can have direction uh, leads us to a concept in physics and math called a vector.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
All right, so that description of a vector is actually really close to the description that we're going to be using. We'll just do so with a little less pelvic thrusting. So vector in this class, we're going to define as a quantity that includes both direction and magnitude. Direction, like I said before, is usually going to be indicated by a plus or a minus, at least when we're talking in motion here. And magnitude is how big of a speed or a force we are talking about. So typically we're going to draw it using an arrow because an arrow is able to describe even more directions than a positive negative can. And then the length of the arrow can indicate direction. We're going to get back to this a lot more when we get into forces and drawing all the forces that are acting on an object. But for now, just know that there are some quantities that are always going to be vector quantities where direction matters. But there will also be some quantities that are what's known as a scalar quantity. A scalar quantity is something that doesn't have direction. So, for example, displacement is our vector quantity, and distance is our scalar quantity. So, a lot of times there are complementary examples here where one's a vector and one's a scalar. Velocity is our vector, speed is our scalar, but then we'll also see some other ones later on this year called force. Force is always a vector. It matters which direction you are applying that force, but energy is always scalar. You can't have negative energy. Energy can be acting in any direction, but it's still always going to be a positive quantity. So know that vector quantities can be negative to indicate direction, but scalar quantities are only ever positive. So if we're gonna then take this idea of a velocity, a speed with direction, and plot that for a couple different examples of motion, we can create what we call a velocity versus time graph. So similar to the graphs that we saw in the last video, now instead of displacement on the y-axis, we're gonna be graphing velocity here. And notice the axes are set up a little bit differently. We are gonna have the potential of negative velocities because velocity has direction. If it's going backwards, we have to assign that direction with a negative symbol. So here, if I have an object that isn't moving, place an object on the floor and leave it there and watch it over time, It's never moving, so its velocity is always zero. Pretty boring graph here. So I can just draw a line there saying, hey, it's not moving, no velocity, 0 meters per second or miles per hour, whatever your units are. Now let's actually put it in motion here, and this is how we're going to describe the creation of this graph. In the last video, we talked about stroboscopic photographs, or a dot diagram, showing that as an object moved, we can place a dot or a capture at every position it is at a certain time interval. So if we do that, we allow this to move, and then every second place a dot where it is, we can see how much it changes from 1 second to the next. The amount that it changes, I'm representing here with a vector, with a quantity represented by an arrow. And that's showing that over that first second, it goes 1, over the second, it went 1, over the third, 1, 1, 1, all the way up. That is our velocity. That's how many meters, if we're going to call this meters, per second this object is traveling. To place that on this graph, I'm going to just take those arrows and put them in their respective times. So the first second, second, and so on. And notice that since this was constant motion, we have a very consistent graph always at 1 meter per second, because at every interval of seconds, that ball or that object traveled 1 meter. If instead I have the object moving backwards, then the change in position over time is always going to be going down because it moved downward, in this case, still 1 every second. Now, if I wanted to plot that on my velocity graph, these downward arrows are going to dip below that x-axis and take a position here at -1 meters per second that entire time, which indicates that it has a speed of 1 in the negative direction. But oftentimes we'll have more than one object that's happening. So if we have two objects, one moving slower like the red one and one moving faster like that green, we can graph the red one in the same way that we did before. Watch it travel, put a dot every second, and then use a vector quantity to show its change. We can do the same thing for the green dot. Notice here that the change per second is larger. Every second there's a gap of 2 meters, which means that when we place this on our velocity versus time graph, that red is traveling at a constant 1 meter per second the whole time, but the green rises up a little bit higher. That's going to be at 2 meters per second. And had it continued moving, if we had more space here, we could have shown it for that full duration of time. But here, since we ran out of room, we just ended it where we were stopping the motion that we could see. So now let's look to see what happens if an object is changing its velocity. Because for all of those examples, we had a constant velocity the whole time. It was never changing its position or changing its velocity, how fast it was getting. But if we had something that was speeding up, so getting faster the whole time, our dot diagram, our captures, would look something like this. Notice as it's going faster and faster, there's a larger gap every second, which means that if we're going to draw a vector, an arrow representing the velocity for that second, that vector gets larger and larger as well. So the first second, we have a pretty small velocity, and the last second, we have a very large velocity. If we move this over to our graph, taking their spots in the corresponding seconds, you'll notice something interesting here. That this is actually a linear velocity relationship where the velocity started out pretty much not moving and then gets faster and faster and faster with ever progressing second. You may remember that the displacement versus time graph was this nice curve as we are graphing the position here. But here we are graphing the change in position per time, and we get a linear graph showing that it is speeding up. And this is linear because in this case, it is a constant velocity. And we'll talk about that in a later video, how we can describe its change. Now, just a quick note, for all of these simulations and these animations, this is being presented in a vertical axis. This could also be horizontal. If you were accelerating or getting faster in your car, you could graph that in exactly the same way. You just have to define which direction is positive and which direction is negative. So if I am in my car and I'm saying that positive is what's in front of me, as I'm speeding up, I could make a diagram like this. You could just imagine that you're looking at it from a bird's eye view, and then the same picture would show up if you were to graph it. If I wanted to show speeding up but in the negative direction, so the object starts away from 0 but moving towards 0 while speeding up, my graph looks something like this. I'm still starting slower, so our velocity vector starts small and get bigger and bigger as the spacing increases. But now, since all of this motion is downward, if I plug this into my velocity side, we know that it's going to dip into the negative part to indicate that it's moving in the negative direction, where it starts out with a small velocity and ends up with a big velocity, but all of them are pointing downward, which means that speeding up in the negative direction gives me a graph that looks something like this. Now, this is one of the trickier graphs for people to conceptualize because our general familiarity with graphs is we look at the slope and we say, all right, the slope is moving down. It must be going down, slowing down in this case. But here, the problem with that thinking is that now we're in the negative part of the graph. So speeding up just means you're getting away from 0. So if we wanted to look at a couple different graphs here, we know that these two are similar because you get faster as you get farther and farther away from 0. So both of these graphs are showing an object speeding up, even though that isn't immediately intuitive to us. It's speeding up because we know that 0 velocity, this center line here basically, is the slowest you can move. And as you get away from that, it means you're getting faster. So if that's what it looks like to speed up, let's look to see what it looks like to slow down. If we're moving in the positive direction, moving away from 0, and starting fast and getting slower and slower and slower, our gaps get smaller as it's traveling, as we're tracking its position per second, which means that our velocity gets smaller and smaller as well. If I plug that into my velocity graph, these larger velocities start us off, and we get a graph that's decreasing like this, moving closer and closer to 0 until it finally comes to a stop. I can also show an object slowing down, moving in the negative direction. To do so, it's going to start very positive here and moving downward, but at the same time slowing down, which is kind of a weird graph to look at because if we thought of this as a ball falling down, it wouldn't really do that. So maybe imagine that it's an elevator coming to a stop, or a yo-yo, or something on a spring that's eventually settling to a 0 point. That it's slowing down as we decrease here in position, which means that we start out with a large negative velocity, and we end up with a velocity basically 0. To put that into this graph, our large negative velocity and our velocity close to 0 gives us a graph that looks like this. So again, this is conceptually challenging for us because it looks like the graph is going up. But what the graph is doing is it is starting in the negative but getting closer to 0. To think about what that means, 0 means not moving, so it is actually slowing down. It's just moving in the negative direction the whole time. So if I show you 4 different graphs, the 4 graphs that we just saw with changing velocity, you should be able to answer these questions. So first, which graphs represent an object that's moving in the negative direction? A, B, C, or D, or some combination of them. If there's more than one correct answer, please mark both. All right, an object that's moving in the negative direction simply means that our velocity is negative. The way that you figure out if a velocity is negative is just by reading the graph. Velocity is the y-axis. So everything above 0 is positive, everything below 0 is negative, which means that C, an object, is moving in the negative direction, but so is B. Both of these are moving in the negative direction because the graph is always below 0. It's never moving in the positive direction. Now, which graphs represent an object slowing down? Again, A, B, C, or D, or some combination. There's more than one that is correct. So here, an object that's slowing down is an object that's starting away from 0, but getting closer to 0. So A is an object that's slowing down because it starts with a velocity of 3 meters per second and ends with a velocity of 0. But at the same time, B is also slowing down. It starts with a velocity of -3. So it's moving in the negative direction really fast, but then slowing down to a stop. Okay, so remember, that is one of the hardest things in this entire unit, is being able to interpret the motion that's being shown in these velocity versus time graphs. So then how can we describe that change in velocity? When we talked about a change in displacement, we talked about that as velocity. But if velocity is changing, that must also have a word, and it does. Change in velocity, we talked about as position over time, basically speed with direction. But if we are changing our velocity, it means we are accelerating. So an acceleration is a change in velocity over time. It actually keeps going. If you take or have taken calculus, you might be aware of the idea of a derivative. Velocity is just the derivative of distance or displacement. Acceleration is just the derivative of velocity. But you could have the derivative of acceleration. A change in acceleration is something called a jerk. So you can define how fast acceleration is changing. We're not going to get into that. This is as far as we're going to go, and that's totally fine. So acceleration is defined as a change in velocity over time. So let's unpack that definition a little bit, because there's actually three different types of acceleration if we say acceleration is just change in velocity. Change in velocity could mean that you're speeding up. Change in velocity could also mean that you're slowing down. So we can use this umbrella term of acceleration to describe something that's coming to a stop. It is accelerating. It's just accelerating, getting slower. You might hear, or you might even hear me use the word decelerate. That is also fine, but know that that still falls under this umbrella term of acceleration. That's just change in velocity. So both of these are examples of changing the speed. But if you remember, the acceleration is a change in velocity. And there's two parts to velocity, speed and direction. So you could also accelerate if you kept the speed the same, but you changed your direction. We're going to get into this in our unit of circular motion and talk about centripetal acceleration. Right now, for this unit, let's focus on these top ones, speeding up and slowing down. And the most common example of speeding up that you are probably thinking of or aware of is trying to accelerate in your car. Speeding up, you're hitting the gas pedal, you're trying to go faster and faster. And this is a picture of my car. I drive a beautiful silver Toyota Matrix, and it can go 0 to 30 meters per second, which is about 65 miles per hour in a whopping 10 seconds. Um, and for me, I'm pretty gingerly pressing on that accelerator, so it takes a little bit longer than that even, because it makes pretty bad noises. If I were to upgrade my car to this beauty right here, it would only take 2.5 seconds to get to the exact same speed. Notice that these two are very different because they have very different slopes that we'll see in our next lesson, that you can define the acceleration as just being the slope of a velocity versus time graph, is how fast your velocity is changing. Here, the slope for my matrix is much less than the slope here, which means it has lower acceleration, which ultimately, when we get into our unit of forces, is connected to how much force it has, because there is less horsepower on my matrix. And then one last aspect here is when we talk about acceleration, there are some tricky things of direction being part of it. And remember, direction in this case, we're going to use positives and negatives because it's a vector quantity. So if you have a car here traveling in the positive velocity direction, and your acceleration is also in the positive direction, think of that acceleration as being the direction that the force of the engine is pushing. These two together are going to cause you to speed up. You'll get a graph that looks something like this. A positive acceleration, speeding up. You could also be moving in the negative direction and have your acceleration also in the negative direction. So it's like your car is pointed in the negative, and acceleration is also pointed in the negative because that's the direction of the engine applying the force. That is still going to make you speed up, even though technically that's a negative direction for your acceleration. So that's a negative acceleration causing you to speed up. These are the graphs that we talked about for that, for displacement versus time and velocity time. So we would call this scenario like the foot on the gas. So the car is pointed one direction and the engine is pushing it in that same direction, causing it to move faster. The opposite of that is, say you have your car moving in the negative direction, but your acceleration, the direction of the force is opposite. So you could think of that as being a ton of wind pushing you backwards, or even your brake applying a force in the opposite direction of your motion. That will give you a positive acceleration, but causing you to slow down. Likewise, you could be moving in the positive direction, negative acceleration, causing you to slow down as well, just because it's counteracting. We call this the foot on the brake. When the acceleration is opposing the motion, then you're slowing down. So it's not enough to just think of a positive acceleration or negative acceleration. You have to factor in the direction that the object is already moving. Because you could, for example, drop a ball and it's moving in the negative direction, but it's getting faster. It's getting faster because there's also a negative acceleration causing it to speed up in the negative. We'll continue talking about this because that's kind of a weird concept to really wrap your mind around. So, in summary, the main takeaways for our lesson today, you should be able to describe the difference between speed and velocity. One is a scalar and one's a vector because it has direction and can possibly be negative. You should also be able to compare between a vector and scalar quantity in general. So whether it's speed and velocity, whether it's distance and displacement, or eventually energy and force, you should know what the difference is and what it means. You should be comfortable plotting constant velocity on a velocity versus time, as well as changing velocity, something that's accelerating, speeding up, or slowing down on a velocity versus time graph. You should be able to use velocity versus time to identify if it's speeding up, slowing down, or positive or negative direction. And then you should be able to define acceleration in terms of velocity. In our next lesson, we're going to look at different ways that you can use these graphs to calculate other things and start putting numbers to all of it. But for right now, you should be very familiar with just describing the motion from one of these graphs.